online part of our conference, and the first talk this afternoon is by Peter Melentijevi from Belgrade. So please start.
Okay, thank you for the invitation. In fact, now I'm in Sochi at the another conference. Sorry for this date, 22nd of June, because yesterday when I was doing with these slides, I completely lose my tech files, and I forgot to change the date. So this is the last version that I had from yesterday. I will talk about LP norm of truncated Riesz transforms and an improved dimension-free estimate for maximal Riesz transform. We will just revoke the definition of Fourier transform, which we will exploit here. Some of authors and mathematicians use the second definition without 2 pi's in the exponent of exponential function, and there is a constant in front of the integral. That is why we use this in order to does not have this constant in front of the integral. As it is very well known, the inverse Fourier transform, which composed with this transform both from the left or from the right gives identity, is of very similar resemblance and as f hat, but it has this looking f with inverse hat is in fact f hat applied to -6. Let us recall the definition of Riesz transforms and its truncated version and maximal version. We consider tempered distributions Wj on Rd, which are defined as it is given here. So we have this constant and then limit as epsilon tends to 0 for this integral. So we integrate the function phi along this function yj over modulus of y on power d plus 1. The Riesz transform, J Riesz transform of f is given as the convolution with this distribution. So it is convolutional type singular integral, and along with this very well-known transform, which is a generalization of Hilbert transform from one-dimensional case, we will also consider truncated Riesz transform, which is of the very similar resemblance, but we will not have this limit. On the contrary, while we consider this limit of truncated Riesz transform and get what is called Riesz transform, we will also consider the supremum of t for a fixed function and fixed x and get maximal Riesz transform. From this early definition, it is very easily to see that this maximal Riesz transform is point by point not smaller than Riesz transform from fixed f and fixed x. Riesz transform are Riesz transforms are in fact Fourier multipliers that we can see from the first formula on this slide, and it is something which we exploit further. Well, we have this point by point inequality, which can be then translated to some norms of both Riesz transform and maximal Riesz transform. If we want to consider maybe the inverse inequality in some norms, then we will first find the result of Matteo and Verdera, which proved this converse inequality in LP norm. And it is given by this formula 1. LP norm of maximal Riesz transform can be controlled with some constant multiple of LP norm of Riesz transform for all f from LP on RD and for every p between 1 and infinity. What is important here to say that they, oh, maybe I'm not sure, but it seems that they did not prove this for p equal to infinity, which we will see that really holds. And this constant c depends both of p and d. It can be why this result is not trivial, because the similar result in one-dimensional case follows very easily from Kotlar's inequality, but here it is not the case, because in Kotlar's inequality for Riesz transform we have, I can say, the first summand from the left, which from the right hand side, which will be the appropriate one, which with which we can work and prove the similar inequality. But unfortunately, the second summand is something with which we can do in the one-dimensional case, but not in a two-dimensional case. In the same paper, Matteo and Verdera, on the contrary to the case of Riesz transform, proved that while the appropriate result for L1 case with L1 norm on the right hand side and weak L1 norm on the left hand side does not hold, the same is true for Bjorling transform, and this statement follows very easily from refined Kotlar's inequality for Bjorling transform. It is this inequality which says that maximal Bjorling transform is controlled by a Hardy-Littlewood-centered maximal operator applied to Bjorling transform. Here I have the sketch of proof. I think that it is something which for which we do not have enough time, but it is something that shows that this can be this will be a consequence of the pointwise inequality with S any constant which is greater than 1. We have these two invariances, translation and dilation invariances. Translation invariance gives that we can just prove this for x equal to 0, dilation invariance t equal to 1. And then if we consider this definition, we will represent this integrand along f as a Riesz transform of some function. This is something which is possible. Also, we can see what is it. And then if we I have a problem to okay, and if we represent this integral, the sum of two integrals, we can estimate the first using Hölder's inequality, while for the second, this is it. While for the second, we will use this pointwise estimate for h. So we must inspect what is h in our equation, and then we will give slightly better inequality, but along with the first inequality, we just give what we want. Okay, the motivation for our investigation are some generalization of this result. I will just mention this result of Matteo Verdera, Orobit, and Perez which gives the similar estimates for maximal singular integrals in terms of singular integrals. So much general result, while dimension-free estimates for Riesz transforms in L2 setting by Wrobel and Kucharski is something which is important here to us. They also proved dimension-free not only L2 but LP estimates, and not only for the first order Riesz transform but for higher order Riesz transforms. What we prove is, in fact, slightly general results with improved dimension free estimates, and it is something which depends on more sharper estimates than that used in Wrobel-Kucharski paper. In fact, their proof depend on estimates for Bessel functions, which appeared in their representation of truncated Riesz transforms, and Littlewood-Paley decomposition. This is something which was exploited in Bourgain's very well-known paper on maximal operators associated to centrally symmetric convex bodies. In fact, they found a formula for certain operator which translates Riesz transform to truncated Riesz transform. It is very important here. What is our motivation? Is that maybe this maximal operator, as it is the case for Hardy-Littlewood maximal operator, is not much bigger than Riesz transform in LP norm if P is for example, equal to 2 and then bigger. It can be proved, even though it is not stated not only in our paper, but in many other papers, that these constants, if in dimension-free bounds, that they are in fact, it is a function which is decreasing on P. So for our question, the question is no, yes, it is much bigger if P is very close to 1, while, for example, for P equal to 2, it is just some small constant. We will prove this bound for P not not smaller than 2, and only for first order Riesz transform. And this is what is stated in our result. For every dimension D bigger than or equal to 2, and for P bigger than or equal to 2, we will have the following bound. So this is much better than bound of Wrobel and Kucharski, as you can see. But they did not intend to prove very sharp inequality. They intend just to prove that it is a dimension-free bound. Okay, the main advance in their paper, in fact, is that there is the operator which is defined as multiplier on L2 space with dsm. What I did not say here is that this function J is Bessel function of the order D over 2. Okay, also we will consider the appropriate maximal counterpart to this in fact family of operators. So for the fixed f, fixed xi, we will have supremum of modulus of all MT. And why we consider this operator? Because of its crucial property that it sends Riesz transform of function f to its truncated version. And hence, this Kucharski-Wrobel lemma, in fact, gives us that the best constant in this inequality with LP norms for Riesz transforms and maximal Riesz transforms is in fact equal to LP norm of maximal operator M star, which is associated to this family of radial Fourier multipliers. Okay, so we need to handle this operator MT or its maximal counterpart. Okay, this is a very small sketch of proof. In fact, we can see what is chi j of t. So this is in fact truncated kernel of Riesz transform, and then because of this this property of chi j of t, we see that considering it on frequency domain, it is just multiplying on the frequency variable, while kj01 is equal to xj multiple of kx, where kx is something which is radial. We can find what is k hat. It is easy to find for radial function. Finding its Fourier transform is something which can be calculated as an integral over the unit sphere, and then after change of variability, some integral over the interval of 0 to 1 with some Bessel functions, and then we know this multiplying on the space variables is in fact something which is finding derivative, partial derivative on jth variable on frequency domain. Okay, it is something that is not written here, unfortunately. And we will see that for this radial Fourier multipliers, there is a very general result of O'Share and Caro. I was surprised when I was searching papers with possible general results on radial Fourier multiplier, that this theorem is not so well known, even it is very, very general, very strong, and it gives even its very special cases are, in my opinion, very good results. But this is it. If we consider the similar truncations for some radial kernel in L1 space, then for all dimensions bigger than 4 and P is bigger than 2, we will have the following inequality. Okay, we will see later why I put this constant for all P, because when we estimate this quantity, we will have two summands, and for the first summand, this constant is even the best possible. Also, we will see that this result cannot be proved for P smaller than 2, and it is not only consequence of the proof, but there are very good examples for which this is not the case. Also, what is GT? GT of x is a function t on minus d, g applied to x over t, very well known. So this, if we consider the Fourier transform of this convolution, it will be some multiplier. This will be multiplier. We will have GT hat multiple of f hat. Okay. We will, for example, we will see that this theorem will not hold if we want to apply it for example, spherical maximal operator. So this gives very good estimates for p not smaller than 2, but for p smaller than 2, it even does not hold. So it is this is the best possible result in this setting. I will sketch the proof of this theorem because we will do the same for our specific kernel, and we will see what is the kernel in our case. So we will use this integration by parts formula in the sense of distributions, and it is interesting that for this first summand, while we consider supremum of this convolution, supremum on T, when we consider supremum of the first summand, we will get this inequality, which is in fact the best with the best possible constant. That is why I wrote before that C of P is equal P over P minus 1, not only 2, because this is something which is true for all P's. Also not for P not smaller than 2, but for all P. This is something which can be considered as right maximal function on the real line. Okay, for the second term, we will use, in fact, this is Cauchy-Schwarz-Muniakovsky inequality, and this can be further majorized by the integral over the whole real line. For someone who is experienced in harmonic analysis, this is something which is known as Littlewood-Paley G function or square function. Plancherel theorems, in fact, gives that this measurand from the last line at this slide is something which is not smaller than or equal, but it is equal to this quantity, and then we can further calculate this using that G is a radial function. So if we call this G applied to the vector T 0, 0, 0, and so T is because G has G's function on RD, its first coordinate is T, and the rest of D minus 1 variables is equal to 0. If we consider this function phi of T, then Fourier transform of this radial function is equal to this expression. We can see that because GS is something which is equal to S on minus D G applied to X over S, while we have this both dilation and multiplication on the space domain, on the frequency domain, it will be just multiplying on variable, and we will calculate what is this expression S, and then derivative on S of this expression. We will get this, and using Jensen's inequality for this expression, after putting this this expression as we have here, we will find that it is not greater than this expression, which after using Fubini's theorem makes this phi t with some multiple of it, in fact, t on d minus 1 modulus of phi of t will get the L1 norm of function g, and we will have this expression which does not depend on t, and also not only for t, it does not depend on psi, as we can see earlier. Okay. Sorry, in this expression we will not have. Just a minute. I think we will not have this star for the second expression, because this is convolution, which after finding Fourier transform and using Parseval's inequality, this is just multiplication. So this formula does not need this star. So this is f hat of psi needs to be here. Okay, and this is something which can be calculated, and then we found something which is in fact given in Osher-Karot theorem as the second summand. Okay, we proved this in fact for p equal to 2. For p equal to infinity, it is some easier inequality, because L infinity norm of maximal operator is in fact equal to L infinity norm of the operator, but operator is convolutional type, and it's in L infinity norm is not greater than L1 norm of function with which we convolve, and then L infinity function of f, and hence we prove this for p equal to 2, p equal to infinity. Interpolation gives the result with this constant here. So interpolation gives this result. So while we can find here the best constant for p for every p bigger than 1, here we have just estimate for p equal to 2, and in fact with p equal to 2 we have some constant for L2 case, but for L infinity case we does not need this with these two summands. Only we know that L infinity normal maximal operator is the same as the original operator, and we use the interpolation. Okay, this is something which we use in proof Osher-Karot theorem, and we need to see that it can be used in our setting. I will just say that this theorem is very interesting, and for this family of kernels, it gives it is something where we do not need to use Jensen's inequality as in the general setting, but we can find the precise value of this Littlewood-Paley G function, and it is some constant multiple of L2 norm of f. This is in fact the second summand in Osher-Karot theorem, and it gives very good constants. The power t over p is missed here, and also here for this is Hardy-Littlewood maximal operator. This is spherical maximal operator. The second example is also good because it gives us why in this setting, this theorem is the best possible because spherical maximal operator is not bounded in every dimension for all p bigger than 1. It is bounded only for p bigger than d over d minus 1. So it is a good example why this theorem cannot be not only proved but cannot hold in this case. And what we have done here is that this MT, which had appeared in Kucharski-Wrobel paper, we see that it is a convolution operator with this phi t. So we found this inverse Fourier transform. It is not a Fourier transform in L1 as a Fourier transform of an L1 function, but it is a Fourier transform in the sense of an improper integral. And because this function, because M is L2 function, while this is L1 function, inverse Fourier transform still can be found. So this is the kernel with which we convolve our f in order to find the best possible bounds for maximal Riesz transforms in terms of Riesz transforms. It can be found using direct calculations or using the properties of Fourier transform that L1 norm of this phi t is equal to 1. And this is something which is very important here. If function is bounded, then we can maybe find the smallest possible radial decreasing measure and prove this, prove our theorem by using usual Hardy-Littlewood maximal operator, but unfortunately for t for x which modulus is near t, this function is not bounded. Hence we use another approach. In fact, it is approach with using Gaucher-Carreau approach for general radial multipliers. In fact, we have a fortune that our function, phi t has L1 norm equal to 1, which gives this LP contractivity of truncated Riesz transform, and hence it gives this inequality for truncated Riesz transform as an operator from LP to LP. The converse bound can be proved using an argument similar to the argument from Lang's paper, where this is proved for one-dimensional Riesz transform, or as it is known by the name Hilbert transform. And we proved that in fact this truncated Riesz transforms has norms equal to LP norms of Riesz transforms, as was found by Ivanets and Martin in their very well-known seminal paper. For the rest, for the proof of our estimate, we use, in fact, these calculations to calculate the second term. And we see that since we know what f hat is in fact function m, multiplier m from Kucharski-Wrobel paper, and we can find it as something which depends on dimension, but fortunately this can be seen as some decreasing sequence, and a square root of this expression, which is in fact measurand for the second term in Osher-Karov approach, is not bigger than square root of 1/2. And we get the conclusion for L2 case. For L infinity case, we have constant 1, and by interpolating, we get our result. And that is all that I have to say. Maybe there are some very natural questions which arose from our paper. It is how to find LP bounds for P smaller than 2, because we know that we know from another Kucharski-Wrobel paper that there are dimension-free estimates for all LP with P bigger than 1, but we cannot use this approach, and we do not have. I think that they do not have constants even with very good asymptotical behavior when P approaches 1. Also, they prove the theorem for higher order Riesz transforms, but can we find better estimates? And I just want to say that there are some important places in literature that everyone interested in this should read and see. Thank you for listening.
Mm-hmm. Thank you very much for your talk.
Are there any questions? I see that there are not so much time, but if anyone is willing, I can answer possibly your questions.
You had the Bessel functions in the talk, so they appeared as Fourier transforms of something radial, yes? Or
yes.
And you had function f with subscripts. What is it? This f?
Oh, this phi with subscript.
Yes, this no f to 1. What is it? F to 1. No.
Where is it? Is it here? You think of this expression?
No, not here. When you had the two choices, closer to the end of the talk.
Okay. You think about this?
Yes.
Yes. This is hypergeometric function.
Hypergeometric.
Gauss. Hypergeometric function. So, in fact, the main result, in fact, is that this function, which is inverse Fourier transform or Raoult multiplier, that it can be calculated. It is positive, and it has finite L1 norm, even equal to 1, and fortunately, thanks to the value of L1 norm of phi t, we have that the LP norms for truncated Riesz transforms is equal to Riesz transforms, which was a surprise to us. While also finiteness of this L1 norm of phi makes it possible even not only to find good estimates, but also to consider this inverse Fourier transform, because this inverse Fourier transform at first is not a Fourier transform of L1 function, because M is not L1 function. M is L2 function, phi is L1 function, and then it is very special setting where also inverse Fourier transform theorem about inverse Fourier transform does hold. So that is something very the setting is very special. This is something which cannot be exploited in, for example, setting of even second-order Riesz transforms.
Okay. Thank you. More questions? Nobody raised their hands. So thank you very much for your talk.
Okay, thank you for your invitation. I was honored to be here.